Okay, so if we look at this example with the Chile saltpeter, we have that it's found in Chile and Peru, which mainly consists of sodium nitrate. And the mineral is purified to concentrate the sodium nitrate, which is used in fertilizer and fireworks. So in order to find the purity of a sample of sodium nitrate, the compound is heated with sodium hydroxide, with Davada's oil, alloy which contains aluminium. Reduces the sodium nitrate to ammonia, which is then boiled off and dissolved in acid. And they give us the equation that we need. And the ammonia gas is dissolved in excess sulfuric acid of a known concentration, and they give us that equation. And the amount of unreacted sulfuric acid is then determined by back titration of sodium hydroxide of known concentration. And we've got another equation. So they say a 1.64 gram sample of impure sodium nitrate was reacted with excess Davada's oil alloy, and the ammonia produced was dissolved in 25 centimeters cubed of 1 mole per decimeter sulfuric acid. And when all of the ammonia had dissolved, the resulting solution was titrated with sodium hydroxide, and for neutralization we had 16.2 centimeters cubed of a 2 mole per decimeter sodium hydroxide required. So what we have in that little bit of information, we have a mass in grams of our sodium nitrate. Then we have 25 centimeters cubed, so that's volume, of a 1 mole per decimeter, which is concentration of the H2SO4. Then we also have 16.2 centimeters cubed, which is volume, of the 2 mole per decimeter, which is concentration of the sodium hydroxide. So, calculate the amount in moles of the sulfuric acid present in the 25 centimeters cubed of the 1 mole H2SO4. So, again, we've got volume and we've got concentration. So we can use our equation, C equals N over V. So we want moles, which is N. So N is going to equal C times V. The concentration was 1 and the volume was 25, but 25 centimeters cubed, and we need to convert that to decimeters cubed. So we divide it by 1,000 to go from centimeters to decimeters. And when you type this into your calculator, you get 0.025 moles of the H2SO4. So now the next question says, calculate the amount in moles of the NaOH present in the 16.2 of the 2 mole NaOH. So we've got volume and we've got concentration. So we can say N equals C times V, and the C is 2 and the V is 16.2 centimeters. So I've got to convert that to decimeters by dividing by 1,000. And when you type that in your calculator, your answer is 0.0324 moles of the NaOH. So now it says use your answer in 2, which was the one we just calculated, to calculate the amount in moles of the H2SO4 that reacted with that NaOH. So now we've got the moles of NaOH. So now we look at our information, and our equation says the NaOH to the H2SO4, the ratio was 1 to 2. So if I have the moles of NaOH, that represents 2. And now I want the H2SO4. So that is half the amount because it's 2 to 1. So I can say my ratio is 2 to 1. So I'm going to take the amount of moles of the NaOH, the 0.0324, and I'm going to halve it by dividing it by 2 because of the ratio. And I'll get an answer of 0.0162 moles of H2SO4. Okay, now it says use your answers to 1 and 3 to calculate the amount in moles of H2SO4 that reacted with the ammonia. So, in 3, this is the amount of H2SO4 that reacted with the sodium hydroxide. In 1, this is the amount of H2SO4 that we originally had, where the ammonia was dissolved in it. So the ammonia was dissolved in this first H2SO4, and then whatever was left over was reacted with the NaOH. So the difference between the two would be what reacted with the ammonia. Because first we took this original concentration of H2SO4, dissolved the ammonia in it, and that reacted. And then whatever was left over was reacted with the sodium hydroxide, which we've then calculated. So we're going to take the original minus what was left over to find what was reacted. So we're going to take our 0.025 minus the 0.0162 to get an answer of 0.0088 moles. So now we have the amount that reacted with the ammonia. So then the next question says, use your answer in 4 to calculate the amount in moles of the NH3 that reacted with the sulfuric acid. So now this was the moles of the H2SO4. So my equation says that I had H2SO4 reacting with ammonia, and that's 2 to 1. So if this is the H2SO4 moles, and it reacts in the ratio of 2 to 1, that means I had double the amount of ammonia as H2SO4. So over here, I'm going to take those moles that I just calculated, and I'm going to multiply it by 2 because my ratio is 1 to 2. So I'm going to say 0.0088 times 2 to give us 0.0176 moles of the NH3. So now it says use your answer that we just calculated in 4 to calculate the amount in moles of NaNO3 that reacted with the Duvardis oil alloy. So now I'm going to look at my information again. And now I've just got the amount of NH3 from here. Now I can look at my other equation and I can see the NH3 there, the ratio says 3. And I want that for the NaNO3, which is also 3. So the ratio is 3 to 3, which is exactly the same because those are the same numbers. So it's exactly the same as saying ratio is 1 to 1 because 3 to 3 is the same ratio. So I can take this amount of moles and say it's exactly the same for the NaNO3 because of my ratio being exactly the same. So now that I have the moles of my sodium nitrate, it says hence calculate the mass of NaNO3 that reacted. So I've got moles and I have a formula so I can find molecular mass. So I can use my equation N equals M over mR. I want mass, so M is going to equal N times mR. the number of moles is 0.0176 times the molecular mass. You will look on your periodic table and find the mass for sodium plus nitrogen plus 3 times oxygens, and you should get an overall answer of 85. And when you type that in your calculator, you get a mass of 1.496 grams. So now that we have the mass of the NaNO3, now it says use that answer to calculate the percentage by mass of NaNO3 present in the impure sample. So this was the mass of the NaNO3, and if we look over here, my original mass was 1.64. So if I want percentage of mass, I can take what I have of 1.496 divided by what I originally had of 1.64 and times that by 100 to give us a percentage of 91.2% purity. Okay, so if I look at the next example for calculations, which is different because now we have to find an unknown. So in my sample, it says I've got a 0.17 gram sample of a group 14 chloride, but it has the formula XCl4, and it reacted with water to produce an oxide of XO2 and HCl. The HCl produced was absorbed in 100 centimeters cubed of a 0.1 mole per decimeter sodium hydroxide solution, which was an excess. In a titration, the unreacted sodium hydroxide solution required 30 centimeters cubed of a 0.2 mole per decimeter hydrochloric acid for complete neutralization. Okay, so I took my chloride, I reacted it with water, and I got my equation. Then all that HCl was absorbed into sodium hydroxide, so it reacted with the sodium hydroxide, and then any sodium hydroxide that was left, because it was excess, meaning it had a whole bunch extra, that extra was then reacted with hydrochloric acid for neutralization. Okay, so again, over here, I've got a mass of my sample, because I've got a mass in grams. Then I've got 100 centimeters cubed, which is my volume, of a 0.1 mole per decimeter, which is my concentration for sodium hydroxide. And then the next part in the titration, it required 30 centimeters cubed, which is volume, of 0.2 mole per decimeter, which is concentration of the hydrochloric acid. So the first part says, calculate the amount in moles of hydrochloric acid used in the titration to neutralize the unreacted sodium hydroxide. So I want the moles of hydrochloric acid that neutralized the unreacted sodium hydroxide. So that was the 30 centimeters cubed of the 0.2 mole hydrochloric acid. So I've got concentration, I've got volume, I can find moles. So I can say number of moles equals C times V, which is going to be 0.2 times 30 divided by 1,000 to go from centimeters to decimeters. And that will give you an answer of 6 times 10 to the minus 3 moles. Then it says write an equation for the reaction between hydrochloric acid and sodium hydroxide. So we know that acid plus base makes salt plus water. And that equation is already balanced, so I can leave it as it is. And then it says calculate the amount in moles of the sodium hydroxide that was neutralized in the titration. So this is the amount of HCl from the titration, and now I want the amount of NaOH. So I can use this equation that I just made, because HCl to NaOH is 1 to 1. So my ratio being 1 to 1 means I have exactly the same amount of moles of NaOH as I did HCl. So it's going to be 6 times 10 to the minus 3 moles. So this was the moles of the HCl. This is the moles of the NaOH. Then it says calculate the amount in moles of the sodium hydroxide that reacted with the HCl produced by the reaction in equation 1. So now, if I look, equation after equation 1, it says the HCl produced was absorbed by 100 centimeters cubed of the 0.01 sodium hydroxide. So that's what I want, because I want the moles of the sodium hydroxide that reacted with that original HCl. So I'm going to say N equals C times V. So my concentration is 0.1, volume is 100, and I'm going to convert that to decimeters by dividing by 1,000. So I end up with a number of moles of 0.01. Okay. Then it says calculate the amount in moles of HCl produced by reaction in equation 1. So I have the original amount of moles that absorbed the HCl, and I have the amount of moles of sodium hydroxide after the titration that was left over. So what I need to do to find the amount that reacted is going to take the original that I have minus what was left over, because the difference is what reacted. Because I reacted the HCl originally with the sodium hydroxide, and then whatever was left was then titrated with the hydrochloric acid. So just like in the previous one, I'm going to take the original amount minus what was left over to find what had reacted. So you see all these chemical calculations all follow similar patterns. So I'm going to take the 0.01 that I originally had minus the 6 times 10 to the minus 3, and I'll get an answer of 0.004. Because that's the difference between them, so that must be what reacted. So that gives me my answer in moles. So then the next question, it says calculate the amount in moles of the XCl4 in the original sample. So I just calculated the amount of HCl in moles for the original reaction of equation 1. So I have the original HCl moles, and I look at the ratio, there is 4 to 1. So I have the 4 moles of the HCl. So if I want the moles of the XCl4, it's going to be divided by 4, because there is 4 times as many HCl to get there. So I'm going to take the moles that I just calculated of my 0.004, and I'm going to divide it by 4, because my ratio is 1 to 4. So when I do that, I get an answer of 0.001 moles. And now, next question says, calculate the molecular mass of that XCl4. So I have the moles. I'm already told the mass. So I can use my equation for number of moles equals mass over molecular mass. And I want the MR. So the MR is going to equal mass over number of moles. So the mass is 0.17 and the number of moles is 0.001. So when I type that in to my calculator, I get an answer of 170. And now it says calculate the relative atomic mass of X and suggest its identity. So this is the molecular mass, and that represents the X and 4 Cl's. So I can say the 170 for the molecular mass is going to equal my X plus my chlorines, and there's 4 of them. So I'm going to say 4 times, if I look up the mass of chlorine on the periodic table, it's 35.5. Because remember, when we calculate molecular mass, we add all the atoms together and multiply each one by what they have. So if I say 4 times 35.5 on my calculator, I end up with an answer of 142. So if I take this to that side and subtract it, I'll end up with an answer for X of 28. So now the atomic mass of X is 28. And if we look on the periodic table for a mass number of 28, we find that it matches silicon, which makes sense because we were told it was a group 14 chloride and silicon is in group 14. So then we know that our answer is correct with all of our calculations. Okay, so as long as you have your periodic table to find the masses of things like that, all your calculations always go in a similar fashion of finding one thing of number of moles, using a ratio, finding another, finding a difference between them for what reacted to find the thing that we want. So as long as we can get the hang of that and to know what we have in terms of units, because we always need to find number of moles, because that's the common thing. Once we have moles and we have a ratio, we can find anything that we need. So once we can practice doing that, then chemical calculations will become a bit easier.